Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammmad Taqiyuddin with Atras. Matric number 177735. This video is the continuation for the last presentation video, last semester presentation video for FFP project. The title of this project is the study of an in-house membrane electrode assembly on reversible fuel cell. So for the introduction of this project, I will skip it because it's the same on fuel cell as the last presentation. I will go straight to problem statement. So the first problem statement is the designing of a membrane electrode assembly for reversible fuel cell. The next one is the use of different catalysts on reversible fuel cell. I want to see whether different catalysts can be used on reversible fuel cell or only specific catalysts can be used on reversible fuel cell. The last one is the performance of different catalysts on reversible fuel cell. So the objective of this project, the first one is to fabricate an in-house membrane electrode assembly. The next one is to analyze the different type of catalyst performance on reversible fuel cell. So the methodology, it is divided into 4 parts. The first one is the membrane treatment. Next one is the platinum carbon integration, followed by fabrication of membrane electrode assembly. The last one is the performance testing of each type of MEA on reversible fuel cell. The first one is the membrane treatment. This is done to remove impurities in the membrane. So the first one, the membrane is treated with the Atras water for 1 hour. It is then treated with hydrogen peroxide for 1 hour, followed by treatment with sulfuric acid for 1 hour. It is then rinsed with the ionized water, and then the membrane is stored in the ionized water overnight. The membrane is then to be let dry overnight. The next one is the platinum carbon incorporation. This is because platinum carbon comes in powder form. So to fabricate on membrane, it needs to be in liquid form. So the first one, 50 mg platinum carbon powder, 1000 mg ethanol solution, and 532.208 microliter ethanol solution is prepared. This material is then mixed in testing bottle. The mixture is then sonicate in ultrasonic bus sonicator for 15 minutes at room temperature. The picture shown is the platinum carbon ink that has been prepared. The next one is the fabrication of membrane electrode assembly. The treated membrane is placed on hot plate. The temperature is set to 80 degrees Celsius. The catalyst ink is then sprayed or brushed on the membrane. In this case, it is brushed because it is brushed. Next one, after the catalyst ink is dried, carbon cloth is placed on both sides of the catalyst. Teflon sheet is also placed on both sides of the membrane. Teflon sheet is placed to protect the membrane from the heat during the heat press process. So the membrane is then hot pressed for 3 minutes. The temperature is set to 130 to 155 degrees Celsius, and the pressure is set to 10 megapascal. The last one is the performance testing of each MEA on reversible fuel cell. First, MEA is placed inside the reversible fuel cell. The reversible fuel cell storage is then filled with distilled water. The fuel cell is then supplied with electrical energy using hand generator until electrolysis reaction takes place. The measurement of the current and voltage is taken using load measurement box at different resistance for 3 times. This is to reduce the measurement error, the reading error. The last one, the procedure is then repeated using different type of MEA, which is the first MEA is the iridium ruthenium oxide and platinum carbon catalyst MEA. The second one is a commercialized platinum carbon catalyst MEA, and the last one is the fabricated platinum carbon catalyst MEA. This is the setup of the current and voltage measurement setting for the reversible fuel cell. As you can see, it uses load measurement box to measure the current and voltage. Results and discussion. Below shows the fabricated MEA. The picture on the right uses standard procedure, which is heat press at 120 to 135 degrees Celsius. The picture on the right shows heat press at 70 to 80 degrees Celsius. So, standard procedure is used for fabrication of membrane electrode assembly. Previous work shows highest performance output when the membrane electrode assembly is heat pressed at 130 degrees Celsius. The previous work is done on proton exchange membrane fuel cell. Okay. So electrolysis may be not important for the MEA. So the next one, after fabrication, the first sample, which is the figure on the left, when tested on reversible fuel cell, no electrolysis reaction occur for the production of hydrogen and oxygen gas. It is assumed that the nephron membrane may be damaged due to the temperature of heat press. So, nephron solution has an operating temperature up to 190 degrees Celsius, but in membrane form it is lower. This is because due to water content and mechanical size of the membrane. So to avoid this problem, a lower heat press temperature is set, which is 70 to 80 degrees Celsius. The result is as shown in the figure on the right. This is the graph for current versus voltage obtained for iridium ruthenium oxide, platinum carbon catalyst MEA, commercialized platinum carbon catalyst MEA, and a fabricated platinum carbon catalyst MEA. So the highest voltage and current output is of MEA is exhibited by the MEA that use iridium ruthenium oxide and platinum black catalyst, which is the maximum voltage is 0.927 volts and maximum current is 0.499 ampere. Further performance analysis of each MEA is done by observing the fuel cell loss from current versus voltage graph and ANOVA analysis of voltage output. Fuel cell loss is done by observing the activation loss, impedance loss, and concentration loss. The figure below shows the standard current versus voltage graph of fuel cell and the fuel cell loss region. Based on current versus voltage graph obtained, it can be observed that an increase in current results in lower potential voltage, which is controlled by the region of activation, impedance, and concentration loss. Activation loss associated with the rate of chemical reaction taking place at electrode as the current is drawn. From the graph, iridium ruthenium oxide and platinum carbon catalyst shows the smallest activation loss. The highest activation loss is exhibited by commercialized platinum carbon MEA. It can be seen from this graph. The lowest activation loss is the blue one, which is the iridium ruthenium oxide, and the highest is the commercialized platinum carbon MEA. The next one is the impedance loss that shows the resistive and capacitive loss associated with the flow of electron and in electrode and electrolyte. So, since mainly ohmic or resistive show a linear function of the current, thus the voltage law also display a linear behavior to this region. So to identify this region, the impedance loss has a linear shape. So, as can be seen, this is the impedance loss region. So it can be observed that the highest impedance loss exhibited by commercialized platinum carbon MEA, and the lowest impedance loss exhibited by iridium ruthenium oxide platinum carbon catalyst MEA. It can be seen that the fabricated platinum carbon catalyst MEA has an unstable shape for the impedance loss. This is maybe due to error that occurred during fabricating the the MEA. So as can be seen that the lowest impedance, the lowest impedance loss is iridium metal oxide and platinum carbon catalyst MEA. It is assumed that the lower the impedance loss, the higher the voltage output. The last one is the concentration loss, which is associated with inability to transport and maintain adequate concentration of reactant to the reaction site due to clogging when the current is strong. So the lowest concentration loss is exhibited by iridium platinum oxide and platinum carbon catalyst MEA. So overall, the lowest equation impedance and concentration loss is exhibited by iridium platinum oxide. So it is assumed iridium platinum oxide and platinum carbon catalyst MEA. So it is assumed that the highest overall performance is yielded by iridium platinum oxide and platinum carbon catalyst MEA. So further analysis is done by ANOVA analysis. This is to calculate the F prime and F value. F prime value calculated exceed the F prime critical value obtained from table. Null hypothesis is rejected. This shows the voltage measured for every resistance applied are not equal. F value calculated also exceed the F critical value obtained from table. Null hypothesis is also rejected. This shows that between each MEA there is difference that can be observed. Further analysis is done to calculate the difference between each of the MEA. So it can be seen that iridium platinum oxide and platinum black catalyst MEA shows significant difference of average voltage output between commercialized and fabricated platinum carbon MEA. Fabricated and commercialized platinum carbon MEA shows no significant difference in average voltage output from the Turkish metal table. So assuming that commercialized MEA use standard procedure for MEA fabrication, which is heat press at 130 to 135 degrees Celsius, the fabricated platinum carbon MEA is heat pressed at 70 to 80 degrees Celsius. There is difference in heat press temperature, but after calculating in Turkish method, there is no significant difference in voltage output. So this shows that different fabricating parameter or technique shows no significant difference in performance output. This coincides with the previous work, which is by T. Frey and M. Rinaldi at 2004, where they conclude that changing catalyst composition has larger effect on fuel cell performance or reversible fuel cell performance rather than changing the preparation technique. The last one is the conclusion. So an in-house fabricated membrane and an in-house fabricated membrane assembly is successfully fabricated using standard procedure. The heat press temperature is lowered because of error that occurred during fabricating. The highest voltage and current output is exhibited by iridium platinum oxide and platinum black catalyst MEA, and the lowest is the commercialized platinum carbon MEA. Iridium platinum oxide and platinum black catalyst MEA shows lowest fuel cell loss. So the conclusion is that iridium platinum oxide and platinum black as catalyst for MEA has highest overall performance yield. The last one is the recommendation. So the first recommendation is that various other materials should be used as catalysts for MEA to be tested with reversible fuel cell to find the best performance for the reversible fuel cell. For example, the use of graphene material, which is the most useful material to replace platinum carbon catalyst for fuel cell, can be used to measure the performance on reversible fuel cell. The second recommendation is that, according to T. Frey and M. Rinaldi, changing material with same functionality has large effect on fuel cell performance. So, naphtha membrane can also be replaced with membrane that has different material to find its performance different. This is also to find the maximum performance output for the reversible fuel cell. Okay, the last one is the usage of an equipment that can directly produce the current versus voltage graph instead of using load measurement box. This is to reduce the error for data taken. So thank you for your time watching and listening for this video. Thank you very much.